was first introduced to R in my psychology master's statistics course. And we had the option of using R, SPSS, and I picked SPSS because I took a look at the R code and thought, oh my God, no. But since then, I've been converted. I'm now a big fan of R. There are a lot of awesome things you can do with R if you do a lot of statistics in your research. The one thing I'm going to say about tonight's lesson is it's just going to be an overview of sort of basic kind of, here's how to do some descriptive statistics in R, and here's an introduction to inferential statistics in R, and here are some really good packages that I think you should make a note of and, you know, potentially use in the future when you are on your own doing stats in R. What this won't be, unfortunately, is like because we only have an hour and a bit, will be an entire kind of introduction to how to use R, the R environment, variable assignment, how to subset variables, all of these sorts of things. So I'm kind of assuming, it's not going to come up too much, but I'm sort of assuming that you guys understand what a function is. I'm assuming that you guys understand that, like, you know, this is how you assign something to a variable. So I'm assuming kind of like very, very basic knowledge here. If that's not the case, try your best to follow along, and we do have a live stream, I believe, on our YouTube channel of our introduction to R, so you guys can go back, watch that, and then watch this live stream again. So these are the packages that I hope you have all now installed. We're gonna kind of move on and just really hope that you have them all installed. And we have a couple helpers, it looks like. So if you're having any trouble, maybe just sort of raise your hand and someone will come over and try to give you a hand. So what? Oh yeah, the stickies. So okay, red is for I need help, or pink is for I need help. Yellow is for all is good. Okay, so in R, I don't know how many of you know this, but R on its own comes with a couple data sets that you can sort of play around with, toy around with, just sort of example data sets. The other thing is in this car package that we're bringing in, it also has an example data set. So the data sets that we're going to be using today are iris, and that's about like flowers. Wong, that one's about like recovery from concussion data, and MT cars, which is about cars. I know nothing about cars, but it had some kind of useful categorical variables and whatever. So these are the three data sets we're going to be working with. We don't need to dwell on them too much. We'll like kind of get to them, but this is sort of what they look like. So this is the Wong data set. This is sort of about individuals who have had concussions, the number of days since their concussion, how long their concussion was, and then measurements of their IQ, measurements of their age, measurements of their sex. The iris data, this is like the species of flower, and then some information about their petals and things like, I don't even know what a sepal is. And then MT cars, so it has like number of gears and like carburetors and cylinders and all of these things that I have no idea what they mean. So those are the three data sets that we're going to be working with today. So the first thing I'm going to show you is just some basic descriptives. So one thing that you're probably going to want to do is count how many things you have in your data set. If you have a categorical variable, like gender, you might want to count how many individuals fall into each category. So you can get frequencies with the function table. This is a useful little function. So I'm going to call the MT cars data set. So I'm actually just going to list the data sets that we're using so people don't get too The hash is a comment, so it means when I run that code, nothing's going to happen. Iris, empty cars, long, and iris. So table, empty cars. And then I'm going to use $, which, in case you don't know, is how you subset a column in a data set. So I'm going to ask for the column gear. So there are different numbers of gears on different cars, and I want a frequency table of how many cars have how many different gears. So in our data set, you can have a car with 3, 4, or 5 gears. And in the console here, which is where you get your sort of like output, you can see here that there are 15 cars with 3 gears, 12 with 4, and 5 with 5 gears. You can also do cross tabulation with with table, the function table, which is a really useful thing. And all you need to do is give it 2 columns. And again, the columns kind of need to be categorical. So this time we're going to give it gear. This time we're going to give it. So now we're going to have like a 2x2 or 3x2, or I'm not sure how many carburetors, different carburetor categories there are. But now we're going to get something that looks like this. So these aren't the greatest labels. If your variables in your data set are like factors, they're given actual names, then the actual names will appear here. But this is the number of carburetors in any given car, and this is the number of gears in any given car. And then here, contained within here, is a little kind of cross tabulation of the count data of how many cars appear within each cell. So there are 3 cars that have 3 gears and 1 carburetor. So that's kind of like helpful to do. Another really easy one is just the mean. How do we get the mean of any given column of data, any variable, right? So one thing that I should mention is, here, let's just do an example first. This time we'll use the concussion data set, and we're gonna look at verbal IQ, PIQ. Me.rm equals T. And you might be thinking, what am I typing here? What is this? Well, here, let's run this and see what we get. So I'm gonna look for the average verbal IQ score of the individuals who are being measured for their IQs post-concussion. And the mean IQ is 94.96. Okay, awesome. So one thing that I should note is without this means NA, which is missing data in our remove, equals true. You can also write true, T, or you can abbreviate it with T. Without this argument, mean will return a null value if there is any missing data in your variable. So generally you sort of want to put that argument in unless that's not what you want. So that's something to keep in mind. So for a lot of the examples here, we're going to see this sort of NA remove equals true argument added to the end. So median, as you can guess, it's actually pretty similar. We can do cool. What's the median? 94. Okay, so it's pretty close to the mean. The other thing that you might want to do is look for variance and standard deviation. So again, variance, pretty straightforward. You just give it your column of numbers or variable that you're interested in. So we're still looking at verbal IQ here. And we also still want to remove those missing values if there are any. And the variance is 197. What about standard deviation? Again, pretty straightforward, NARM equals true. So these are all just sort of descriptive statistics that might be relevant, things you might want to report in your data set. You can also get like the range. But who thinks this is a little tedious? Raise your hand if you think it's kind of tedious what we're doing here. If you're not raising your hand, I don't know why. Because this takes a while, right? If you want all this information for any given variable, this is not very fast. So I made you guys install this psych package. And what the psych package does is it gives you all kinds of descriptive statistics of about any given variable all in one go. So one really, really useful function is describe from the psych package. So it gives you, here, well, let's just take a look. This time, let's do age from the concussion data set and get some information on the age of the participants. In this case, you don't have to type in the NA remove equals true. It kind of does that by default. So all you have to do is describe and then give it the variable that you want. And if you have a vector, like you just put that in. Here we're calling the age variable, and let's see what it gives us. Okay, so wow, that's awesome. It gives us a lot of information in one go. So it's giving us the number, it's giving us the mean, standard deviation, median, trimmed mean. MAD is median absolute deviation from the median. I have no idea what that is or why you would ever want it, but it's there for you if you need your MAD. There's min, max, range, skew, kurtosis, standard error. So this is a lot of information with just sort of one function, right? So I really recommend if you need a lot of descriptive statistics about your various variables in your data set, just call that psych package in and use the describe function. The psych package also has a lot of other really useful functions. So what if you have age and you want some statistics on age, but you want information on age depending on whether the individual is a male or a female? Well, the psych package has something called describe by. So what describe by is a simple way of generating summary statistics by some grouping variable. So in this case, like I said, if we want to see in that concussion data, okay, we have all of this information on age, but I want that divided up depending on the person's sex. So we can do describe by, and then all we do is, as its two arguments, are the variable we want descriptive summary statistics for, and then the grouping variable. So then we do long sex. Okay, let's see what we get here. Okay, that's pretty awesome. So now we have descriptive statistics by group. Group female, now we have like the mean, standard deviation, median, min, max, whatever, for age for females only, and then we have the same information for males only. So that's a really, really, really helpful. These two particular functions are extremely helpful from the site package for getting a lot of fast summary statistics on your data. Okay, does anyone have any questions about the descriptive stats? Because that's like kind of some basic stuff. I mean, we've gone all the way to MAD, so you know, I don't know if there's anything else you guys want to see, but I think we can move on to some basic inferential statistics. So yellow stickies up if we're good, red, pink stickies up if.
Sorry, I'm just gonna read this.
Try to read this. Okay, any pink stickies? I see a couple pink stickies, and I don't know if that's just pink sticky neglect or actual. Yeah.
Where did you get the long data frame from?
The long data frame is from the car package. So if you load the car package, then it's good. I think I said that at the beginning. So the other two are native to R. The Wong data frame is from the car package. You need to have installed the car package to have that example data set. The other two just work. So if the Wong data set isn't working for you, it's because your car package isn't installed correctly. Okay, so while that's being sorted out, I'm going to move on to the very exciting one sample t-test. Do we need a sec? Increase it even more? At that point, it's like, yeah, I don't think. Okay, are we ready to move on? Cool. So, the very exciting one sample t-test. So this test is, you don't need to load any packages to use this. This is just native to R. And let's use age again. Let's keep using age. And for the one sample t-test, all you have to do is say, okay, this is the variable, and it's automatically going to calculate the mean of this particular variable. And then you need to give it your kind of comparison value, right? So earlier up there, I think the average age was maybe like 31. So let's see if it's significantly different from 30. Because that's kind of close, but not that close. So let's see if we have a significant kind of difference using our one sample of age from our mu of 30. So it's going to give you output that looks like this. And it gives you your t statistic, your degrees of freedom, and your p-value. So in this case, as I said before, the actual mean of x is 31. And in this case, we have a lot of power, I guess. We have 330 individuals. So what we're seeing is a significant difference between our kind of population, hypothesized population mean of 30 and our actual mean of 31. So that's super exciting, but people rarely do one sample t-test. It's not a super useful test. How do we do a two sample t-test? Well, you can probably guess that it starts with the function t-test. So there are two ways to write this out, and it sort of depends on how your data are organized. In our case, what I'm going to do is write out Wong age, and then I'm going to put in a tilde, and that just kind of means like the thing to the left is the descriptive variable, or sorry, it's the outcome variable. And then the thing to the right is the thing that you're grouping it by, or the thing that you're regressing it on, or what have you. So what this means is this is a two sample t-test. We want to see if there are differences in age by sex. Another way to write this out is, let's say you just have like two different data sets, like two different columns of numbers that are just floating around in different places. You could write it like this. So you just put object 1, object 2. And it's going to compare all of the numbers contained within this and all of the numbers contained within this, and then run the exact same test. But in our data set, the data are kind of organized like this. So we can just use this because it's sort of like sex is paired up along the lines of age. So anyways, let's run this and see if we have a sex difference by age. So again, it's giving you the same sort of output, right? You have your t-value, your df, your p-value. Clearly, there are a lot of missing cases in this case. So p-value 0.4, that's disappointingly not below 0.005. So there isn't a significant difference between the group mean ages between males and females in this group, right? So that's a pretty easy one. What about a correlation? Well, you can use core test. So now we're going to call in the iris data set. So let's just look at that again. It has the species, petal width, petal length, sepal width, sepal length. If anyone can tell me what a sepal is, that would be awesome. Are there any plant biologists? Sepal and petal is the same thing?
No, the petal is the complement.
Oh, well, there you go. Okay, so that's the data set we're working with. So let's see if petal length and petal width are in any way correlated with each other. So we write core.test. This is our function, and we want to call the iris data set, and we just write petal length. You also might notice that tab completion is your friend in our petal width. And if you just wrote core, it would actually just give you the correlation value, but core.test is going to give you an actual, like the actual hypothesis test on the correlation value. So I just ran this correlation test. And what we're going to see here, again, is the same sort of format where we see our t-value, our degrees of freedom. In this case, it is significant. So there is a significant significant correlation between petal length and petal width, gives you a 95% confidence interval. Pretty simple. If you want to run multiple correlations, you can actually just put another R in there and then just keep adding whatever. And it'll give you a correlation matrix. Okay, so on to the thing we probably all use the most, which is the general linear model. Oopsie. Okay, so in this case, I'm talking about normally distributed dependent variable. I'm going to talk about non-normally distributed dependent variables later. So again, the formula to regress y on x, so the formula to regress is y tilde x. And the formula just to run a general linear model is just LM. So let's say we want to see if the duration of the coma in any way predicts verbal IQ. Has it had an effect on it? So what we would do is type in the variable name. So in this case, we don't have to subset because we're going to tell the function what data set we're using. So VIQ from the Wong data set stands for verbal IQ. And then we want to regress it on duration. And then we need to tell the linear model function what data frame we're using, which is the Wong data frame. And you run this, and it kind of gives you not a whole lot. So what you want to do is you want to save it to a variable so you can get a summary of your linear model. So I'm going to very cleverly name this variable result. And we can run this, and then we can use the summary function. And yes, you pretty much have to do this every single time. A result. And now we're getting actual useful information. So it's giving us like our intercepts, whatever, what have you. But here's our duration. So here's, we have our estimate. I think this is, yeah, I think it's B. It has standard error, t-value. I think one of these packages actually has a way to ask for data values. Anyways, whatever. And then it gives you your significance, like your p-value right here. So duration doesn't have an effect on verbal IQ, duration of coma. So, okay, that's nice. But what about if we want more than one predictor variable? So you can do the same thing, but this time, let's say we want to see if the duration since the person's been in the coma and the number of days that the person's been in the coma affect the person's verbal IQ. And we want to see if there's an interaction between the two. So in this case, to get like a full kind of factorial situation to get your interaction term and the main effects for both duration and days, you use the tilde notation, and then these are your two independent variables, and you connect them with this little asterisk, which is like a multiplier symbol in R. And that's telling R that you want that interaction term. If you didn't want the interaction term between duration and days, you could just put the plus sign, and it's just going to give you the main effect of duration on verbal IQ and the main effect of days on verbal IQ. But let's just do this for now. All right, cool. And then we want summary. Okay, so in this case, again, nothing is really significant. There's no effective duration, no effective days, no effective duration on days. However, now we know how to do, and you can just keep adding predictors, right? So I could add every single predictor in the model, and it would be like, yeah. Those are pretty much, yeah, page. So you can just keep adding. Okay, but what about ANOVAs? So how do we do ANOVAs in R? So this is actually kind of, I would say, one of the trickier things that I had to learn in R. Because in R, base R is going to give you different results for your ANOVA than SPSS or SAS or anything like that. So I'm going to explain that in just a sec. But I'll show you how to do it first, and then show you how to do it the right way. So ANOVA. So you always have to wrap. The ANOVA is basically, the ANOVA function is just basically like a wrapper for this linear model function. So you always have to wrap ANOVA, the ANOVA function, around your model function. So again, this is just base R we're working with. This isn't really calling any of our packages. So let's use the MT cars data set and do miles per gallon, I think this stands for. And then our predictors, because I guess these are kind of categorical variables. I don't know, a number of years. And then data equals MT cars. We also have actually have the documentation for all of these. I'll put this up later. And transmission, automatic or manual. Okay, so we have two categories there. Gears, I think we had 3 categories. Anyways, so we're seeing if the number of gears or whether your transmission is automatic or manual has any effect on miles per gallon. So let's run that. Object gears not found. Is it gear? So it is. Okay, let's run that again. Okay. So it looks like the transmission has an effect on miles per gallon. It looks like the interaction of transmission and gear has an effect on miles per gallon, but gear itself doesn't. But the thing about this output is if I were to run this exact same example in SPSS right now, you would get different p-values. And the reason is because of sums of squares. So if anyone remembers all the way back to like undergrad, probably when you took your first few stats courses, there are different, I'm not going to explain what sums of squares are here, like explain why one might choose type 1 or type 2 or type 3 or whatever. The point is, pretty much everyone uses type 3 by default. SPSS uses type 3 by default. If you want something that's not type 3 in SPSS, you have to ask for it specifically. Strangely, R uses, I think, type 2 by default. Type 1? You think it's type 1? Well, it's not type 3. So that caused a lot of confusion for me when I first started like trying to run ANOVAs in R. I would like compare my results to my SPSS output and be like, what am I doing wrong? And I wasn't doing anything wrong. I just wasn't using type 3 sums of squares. And chances are that's like probably what you're gonna wanna use unless you have like a specific reason not to. Now, I should also make a note, this is only gonna make a difference to your output if you have more than one, like if it's more than a one-way ANOVA, basically. If you have more than one factor. But just be aware that this is a thing. And if you want your output to match your SPSS output, that most people just don't even think about it by default and just publish their ANOVA results with type 3 sums of squares. So let's just do it that way, because then your supervisor doesn't have to say, hey, I reran your analysis in SPSS or whatever old program that I use, and it's not the same. So how do we get type 3 sums of squares? This is like the #1 question I think that I get ever about like ANOVAs in R. So there is a function called ANOVA from the car package that can give you type 3 sums of squares. So yeah, that's gonna match the output you get from SPSS or SAS. So we can run our linear model the same way. So let's do what we were doing before. Oops, linear model. We have miles per gallon. And then our predictors are, we have transmission and gear, number of gears. And then our data is empty cars. Cool. So let's run that. And this time, instead of asking for a summary of the linear model result, what we're going to do is we're going to call the ANOVA function. We're going to say we want, like, we're wrapping the result of this linear model in our ANOVA function, and we want type 3 sums of squares. What's cool is if you actually want type 2, you can just put in type 2 or type 1. But look at how much our results have changed. So let's just scroll up. So these were our p-values before. And these are our p-values after using type 3 sums of squares. So it definitely makes a difference to your output. What type of sums of squares, like it absolutely matters for the calculation of the results of your ANOVA. So that is how you get type 3 sums of squares. You use the ANOVA from the car package.
Does the ANOVA from base R not have the type argument?
It doesn't, but there are ways that you can set it to type 3 sums of squares, but it's way longer. Okay. So I can show you that code afterwards, because I've done it that way. Like you can set contrast, like you can do, like, yeah, you can do it with base R, but like, why would you? Because look at, like, this is so easy. Whereas I think like when I did it with base R, I like didn't really know what I was doing, and I had like 5 lines of code to do what I could have done in 1, and there's just no point. So that's my attitude. But yeah, in base R, no, there's no just like, oh, type equals blah. There is no such argument. You have to set a bunch of things before you run the linear model and then wrap the linear model in the ANOVA function. So it's like just remember ANOVA with an uppercase is from the car package. Okay, what else do we want to talk about? Yeah, oh, wow, okay, we've run our ANOVA. What about post-hoc tests? So this is another thing that base R kind of like fails at. It doesn't do too well at. There is sort of like a default pairwise t-test that R comes with. So R comes with a default pairwise t-test function. So it's pairwise t-test. It's pretty obvious. And it does exactly what it sounds like. But the reason I asked you to download multcomp, which I think stands for multiple comparisons, is because it gives you a lot more options in terms of multiple comparisons. So, yeah, multcomp. It offers more post hoc options. So it offers things like a 2-keys HSD, I don't know, Bonferroni correction. The documentation is online, so it's actually quite complicated. Multcomp. So if you ever want to like have a look-see at what it can actually do, you can have a look at the documentation. And it'll tell you exactly all of the different options it has. So yeah, a lot of different. But I use 2-keys HSD a lot in my research, so I'm going to use that as an example. So also just makes it a lot easier to do. So let's create another kind of linear model result. Let's do linear model, and this time I want a categorical variable with more than 2 levels. So let's do linear model with petal length. And then species, because in the iris data, there are 3 species of flowers. So we're going to say data equals iris. Okay, cool. So we've got our linear model. We've saved the result. Now, instead of asking for summaries, well, I mean, you can ask for the summary and probably will ask for the summary of the linear model. I mean, in this case, who cares? But well, actually, this should have been wrapped in an ANOVA, so just ignore that. So this is like technically an ANOVA that I'm running. So if I would have wanted to do this, type equals species, and it's significant. So species, there are significant differences in petal length between species, right? So we have our ANOVA result, type 3, awesome. Okay, so we know that there are significant differences between petal length based on species, but we don't know which species differ from which species. So that's kind of what we want to figure out here, and we're gonna do it with our multcomp package. So what you can do is now, this is a total arbitrary variable. You can name it whatever you want. I call it post hocs. But again, you're just sort of saving the results of the post hoc test that you're running here. And this function is kind of weird, and I have no idea what it stands for, but it's GLHT. And then the arguments you want to give it are the result of your linear model. You don't need to put it in the wrapper of the ANOVA. You just give it the result of the linear model. And I have no idea what this stands for. But the key thing here is you type this out, and then what you want to do is say what factor, like what variable you want to investigate and like investigate the differences of, and then what tests you want to use. So species, right? So species equals, and we want a 2-key test. We want 2 keys HSD. So this is just the code you write out to get your postdocs. It's kind of like a little bit like a bit unwieldy, but the key things here is to put your results from your linear model in here. You need to specify the variable that you want to investigate differences in, and then you need to specify the type of the tests that you want, right? And you can, there's probably a help function for, they'll tell you more about it. General linear hypotheses, that's what it stands for. So this is going to tell you what all of the arguments mean. But for now, let's run this. Cool. And then we want to get a summary of the post talks. Oops, post talks. And what that gives us, oopsie, are multiple comparisons using 2 keys HSD. So it compares every, like it makes every single comparison, and then it gives you your standard error, your t-value, and your p-value. So it looks like in every single case, every single species differs from every single species. So Virginica differs from Setosa, Virginica differs from versicolor, et cetera, et cetera. So your p-values are all less than 0.05 here. So they're all significant at like the 0.001 level. Yep. So I'll just leave this on here for a minute. Again, I know it seems kind of a little bit like, ugh, this is a lot to type out, but this actually, in my opinion, is the easiest way to do post hoc tests, and gives you the most options in terms of like what comparisons you want to do. So you can also get confidence intervals. And again, this is coming from the multcomp package by using this confint, this function. So here it's giving you confidence intervals for the differences between the different means. So that's useful. That's something you might want to report. Again, multcomp is a really, really awesome package. It has a lot of different features, but the thing I use it most for is just running multiple comparisons. Okay. We're almost at the end. I have a couple more things to show you. So what if your dependent variable isn't normally distributed? So one thing I do a lot in my research is like logistic regression, logistic binary regression. So how would we do that? So in this case, we don't use the linear model function anymore. We're using the generalized linear model function. So we're not using the function that makes assumptions about like a normally distributed dependent variable, et cetera, et cetera. So I'm using logistic regression as an example, but you could use the same function to do like a Poisson distribution, like whatever you want. So must use GLM function rather than LM. So linear model, again, making all those assumptions about your dependent variable. GLM, not so much, right? So it gives you a little bit more freedom. If you have like a specific distribution that you are expecting for your dependent variable. So one thing I'm going to mention is you don't actually have to write this out every single time. You could just wrap it all in summary if you have no particular reason to save your linear model results. So let's try it that way. Mix things up a bit. Oops. So now we're using GLM instead of LM. So GLM. So let's use our concussion data set. And I want to see if sex, which in this data set is binary, it can be predicted by verbal and performance IQ. So performance IQ, like spatial reasoning, things like that. So we're going to see, we're going to regress it onto Wong. I want the interact. I don't really need an interaction term here, but I don't even know what that would mean. Okay. Oops. Oh, that's fine. Oh, here. And then we tell it what family. So we want binomial because it's, oopsie. Because it's a logistic regression. So I don't know if this, like typing it out this way kind of confuses people. So you can sort of still do it the good old results. That doesn't really matter. Oops. Okay. So this is giving us our logistic regression and our results from our logistic regression. So it's giving us our predictors here. So it basically looks like performance IQ, verbal IQ, or the interaction between performance IQ and verbal IQ in no way predict someone's sex. It's kind of not a super useful example, but there you go. It also gives you like an AIC value, like a fit value. So it's kind of useful, but yeah, you can look this up and do like Poisson distributions, things like that. Okay, absolute last thing before I let everyone go is reliability. So this is probably going to be more relevant to like the psych people in the room, maybe. But if you are administering scale, you might want to get a reliability value of that scale, or you might want to sum across rows. So I'll show you how to sum across rows, and then I'll show you how to get some reliability estimates out of that. Summing across rows is also useful if you have, for example, like a scale, and then you want like a composite value, obviously, right? So you can get Cronbach's alpha from the psych package. So I'm just going to subset iris into a new data frame just to get rid of that the species column, because in this case the data frame or the matrix, whatever, has to be all numerical to get a Chromebox alpha value, right? So I'm just gonna sort of subset it and make a new data set with just the first 4 rows, which were just like the petal length and width and the sepal length and width. And we're gonna pretend that that's part of some psychological measure of something. So new iris. Some of you might not recognize this notation. This is just saying I want like a slice of the first 4 columns in iris. And then this is a handy function called row means. Just do that. And it's literally just going to give you the row means. So you can imagine, again, if you had like a scale with like 10 items and you wanted to sum across and get like a, you know, a total score for each individual, this would be kind of like a useful function to know. So we're almost kind of going back to the descriptive statistics. But let's say you want kind of an estimate of like how well your scale is performing, like what is the internal consistency of the scale. Going back to alpha to get an alpha value, it's actually really easy. You just take your data frame with the relevant variables in it. Again, all has to be numeric. And just use the alpha function and it will give you, oopsie, actually gives you this useful warning. So I'll show you why. Okay. So it gives you the raw alpha. It gives you reliability if an item is dropped, which is a really useful thing. That's something you can ask for in SPSS. It just automatically gives it to you here. It also gives you like item statistics, so the means and standard deviations, whatever. But what it's saying is that some of the items were negatively correlated with the scale. So usually that means you have like forgot to unreverse code something in a scale. So it actually kindly gives you a warning and says, hey, you forgot to reverse code something. But this is how you do reliability, and that's you'd sum across rows and sort of like get a total for some kind of like participant data or anything like that. Okay, it's 7:08. I think that's it. That's all we have time for now. So I'm gonna post this code online. Feel free to email us or post any questions on our GitHub that you might have. Come to our co-working sessions, ask us questions. Again, if you need a little bit more background in just sort of how to use R, how to assign things to variables, how to subset things, those are really useful things that are gonna come in handy when you're doing stats in R. So definitely you guys can watch our previous video on YouTube or contact us for some resources or come to our coders meetings. Okay, so Madeline, thanks.